Hey everybody, so what we're going to do in this video is we're going to go over some of the details we've already discussed when it comes to bond line structures. We want to make sure that you're comfortable drawing accurate representations of molecules just using these crooked lines that we've been using in class. We'll talk a little bit about how the issue of formal charge and showing the lone pairs is important at times when it comes to bond line structures. Review a little bit about functional groups that you have started to hopefully get comfortable with. And then we're going to wrap up a little bit with some of the details of how we have to worry about now, starting with wedges and dashes on our bond line structures. So let me move my face here out of the way. I'll put myself over in the corner here. And so bond line structures, we've already gone into quite a bit of detail with these sorts of representations of molecules. Remember, these are sort of the ends and elbows representation, as I like to call them. So we have here 1, 2, 3 carbons and then a nitrogen. Down here I have 1, 2, 3, 4 carbons in that structure there. Now, we typically will only see the carbons in any structure, setting aside things like nitrogens and oxygens for now. We typically don't draw the hydrogens in bond line structures, although there are times when we do need to draw the hydrogens. For example, here with this nitrogen that has 2 hydrogens on it, we want to put hydrogens when we have non-carbon atoms. So let's make sure we put our hydrogens on nitrogens or on oxygens. Also, there'll be a need to put in a hydrogen, maybe even on a carbon, if that particular hydrogen is important for whatever the conversation is doing about that particular molecule. Of course, we want to make sure things are drawn with accurate geometry, right? The crooked line notation helps us develop the fact that these carbons are sp3 hybridized in this case, and so they're going to have tetrahedral geometry. If we have non-sp3 structures, if we have things like sp2 carbons, as we have in alkynes, we have to make sure that those are drawn in a straight line, that they have the 180-degree linear sp2 shape that they ought to have. Drawing an alkyne like that won't work at this point, okay? That is inaccurate. Now, you always want to show your lone pairs at the times when they're really important for a structure. Maybe they are there so that you can show how an atom gets to a particular formal charge. Or, as will be coming up very soon in our conversations, maybe we need the lone pairs to help us do some resonance structures of a molecule. And so we're going to need to show lone pairs then. So, for example, over here in this structure here, I'm making a point of showing the lone pairs on this oxygen because this oxygen has a negative formal charge. The oxygen here at the top, that structure, that oxygen has a 0 formal charge. Now, of course, I could put in the lone pairs, and I could put in the 2 dots I would need there and 2 dots there, and so I could go ahead and show the fact that I have a completed octet there. But those lone pairs may not be entirely essential just yet, because again, there's no non-zero formal charge there. And speaking of formal charges, we want to continue to get comfortable with showing the formal charge on the specific atom on which it resides. I think from previous chemistry classes, you're sort of used to putting a molecule in brackets and then putting the formal charge outside the brackets. We want to be a little more specific now. So let's put the formal charge right on the atom that it is modifying. Okay, so continue here. Let's talk about some specific cases of where formal charges show up in bond line structures. So we have here some examples of what are called carbocations. Usually, if a carbon is going to carry a formal charge, it's going to carry a positive formal charge, as I'm showing in these structures here. Now, neutral carbons, they will have 4 covalent bonds, and there'll be no lone pairs on the atom. Sometimes, though, carbon will have a formal charge. If it does, its most common formal charge, and the structures we'll be looking at, will be +1. So here are 3 different examples that show carbons with having a +1 formal charge, these carbocations. Now, one of the takeaways we have to start to get when we look at these structures is that these carbocations are subtly different. Specifically, the one on the left here, that carbon that I'm pointing to right now, that is a carbocation because there are only 3 other carbons attached to it, so it has 6 electrons around it, so it is not satisfying the octet, and in terms of its formal charge, that carbon is only connected to 1, 2, 3 carbons, so it has 3 electrons around it. It wants 4, so it has that +1 formal charge. But this carbocation is different than this one, is different than that one. Can you see the subtle difference? Hopefully what you're picking up on is that the carbocation on the left here is attached to 3 other carbons. This carbocation is attached to 2 other carbons and 1 undrawn hydrogen. There's a hydrogen on that carbocation that I'm not overtly drawing in. And then lastly, we have a carbocation which is attached to 1 carbon and then 2 undrawn hydrogens. So we can have carbocations surrounded by different other atoms. And these different sort of levels, as it were, of carbocations, they're going to get their own terminology. Specifically, we will call a carbocation that is surrounded by 3 carbons, this is going to be called a tertiary carbocation, and it's abbreviated with a 3 with a little degree symbol on it. That's tertiary. This second one is going to be called secondary, and it's abbreviated with a 2 with a degree symbol on it. And the last one is referred to as a primary carbocation, 1 with a little degree symbol on it. And we're going to get into some of the details about this later on, but there is also an important distinction amongst these carbocations when it comes to their relative stabilities. As we go right to left, the stability of these carbocations increases. A molecule would rather contain a tertiary carbocation than it would contain a secondary or a primary carbocation. So this is one common structure we'll see when it comes to carbons having a formal charge. What else could we have? Well, sometimes you will have a carbon that isn't carrying a positive charge, but it's carrying a negative charge. This is called a carbanion. So we have a -1 formal charge on a carbanion. How do we get there? Well, we have our carbon, it's attached to 3 other hydrogens, and then it has a lone pair. So this carbon, which is in, of course, group 4, it has 1, 2, 3, 4, 5 electrons around it. So it has 5, it wants 4. That's how we get a formal charge of -1. These are definitely less common, much more rare than having carbocations. Anionic carbons are not very stable molecules. A molecule like this is going to be wanting to react with really the first mildly reactive other molecule it can find itself around. All right, continuing on then. We have to get used to looking at structures and being able to quickly deduce both the formal charge that an atom would have and therefore, correspondingly, the number of lone pairs that would need to be on that particular atom to arrive at that formal charge. So taking a look at the amine here on the left, these are amines, okay? Taking a look at this amine here, note there's no formal charge on the nitrogen. So hopefully you can quickly deduce the number of lone pairs that needs to be on that nitrogen in order to arrive at a 0 formal charge. In this case, it's only going to be 1 lone pair. So by having 1 lone pair there, I have on that nitrogen, I have 2, 4, 6, 8 electrons around the nitrogen. So it satisfied the octet rule. In terms of formal charge, I have 1 electron from the carbon bond, a 2nd and 3rd electrons from the 2 hydrogens, and then a 4th and 5th electron from the lone pair. And so nitrogen is in group 5 and has 5 electrons. So that atom has no formal charge. Taking a look at my second structure, this nitrogen here, how many lone pairs am I going to need to have around it to arrive at an overall +1 formal charge? Well, let's go ahead and take a look. I have, on this nitrogen, I have 1 electron from the nitrogen-carbon bond, and then 3 more electrons around the nitrogen for each of the hydrogens. So I have a total of 4 electrons around the nitrogen in terms of counting for formal charge. Nitrogen's in group 5, it only has 4 electrons around it, so we're going to have that +1 formal charge. Now take a moment then to figure out how many electrons, how many lone pairs will be around this anionic nitrogen here on the far right. Hopefully you're catching the rhythm here and you are thinking that there needs to be not just 1 lone pair, but 2 lone pairs. So let's count it up. I have, 2, 4, 6, 8 electrons, so the octet rule is satisfied. The octet rule was satisfied here as well. So everybody's satisfying the octet rule. And then formal charge, I have 1 electron from the carbon bond, 1 electron for the bond to hydrogen, so that's 2. And then I have 3, 4, 5, 6 as we include the lone pairs. So that's 6 electrons around that nitrogen. Again, group 5, it has 1 more electron than it wants, so that's how we get our -1 formal charge. So you should get comfortable looking at any structure that doesn't necessarily show lone pairs and using any formal charge information to figure out how many lone pairs there need to be. Or conversely, maybe you're not shown formal charges, but you're shown the lone pairs, so you have to quickly deduce how many, what the formal charge would need to be as a result of the given number of lone pairs. So that's kind of what we want to do here on this slide. Can you look at these structures here and figure out how many lone pairs or what formal charge the atom needs to have in order to have everything make sense? For example, this oxygen here, okay, there's no formal charge being shown, but we do have the lone pair. So can you tell me what the formal charge of that oxygen is? Take a moment to figure that out for yourself. And same for this oxygen here that's showing a negative formal charge. How many lone pairs would need to be there in order to determine what the, to arrive at that -1 formal charge, okay? I'll do a couple of these here now, but then the rest of the atoms, maybe you'll take some time on your own and do it. So let's come back to this oxygen here. There are 2, 4, 6, 8 electrons around it, so the octet is satisfied. But now for formal charge, I have 1 electron from that bond, 2, 3 electrons from those bonds, and then 4, 5 electrons from the lone pair. So this oxygen has 5 electrons around it. What group is oxygen in? It's in group 6. So this oxygen is going to have a +1 formal charge on it. So this guy has a +1 formal charge. Let's go over to that anionic oxygen here. How many lone pairs need to be on this oxygen to arrive at a -1 formal charge? Well, I need to have 7 electrons around an anionic oxygen, because 7 minus 6 would get me to, or really 6 minus 7, I should say, would get me to my -1. So then I already have 1 electron from the carbon-nitrogen bond. So then clearly I'm going to need not 1 lone pair, not 2 lone pairs, but 3 lone pairs around that oxygen to get me to where I need to go. So what you should do is, on your own, take some time and figure out what the formal charge of that oxygen is, this sulfur, this nitrogen, and that nitrogen, and then figure out how many, if any, lone pairs need to be on that carbocation, how many lone pairs need to be on that nitrogen, what the number of lone pairs would be for this oxygen and that oxygen as well, and then go ahead and figure out what the formal charge there might be for that phosphorus. So be comfortable working with a given number of lone pairs and what the formal charge should be, or if you are shown a formal charge, how many lone pairs, if any, would be on that particular atom. We'll follow up with this in more detail in class. Okay, so let's talk about functional groups. Now that you should be more and more comfortable drawing bond line structures, we're going to start incorporating not just single bonds, but double and triple bonds, as well as functional groups that arrive due to certain heteroatoms, non-carbons, non-hydrogens. So these different patterns of atom arrangements, right, they're called functional groups. Here are some of the functional groups that were on the chart that we shared with you at the beginning of the school year. And we also want to make sure that you are in the not too distant future. Remember that this R, things like these R's here or these R's here, typically what R refers to is either a non-specific chain of carbon atoms, or in some cases it could also represent a hydrogen if it's not all that important what's hanging off of the main part of the function. With all of the other functional groups. There are a total of 16 for you to get used to. And hopefully, maybe by using some note cards, some flashcards, you can get the hang of these functional groups. All right, so we don't need to talk about functional groups too much. You've already started to look at these. Hopefully, you're getting more and more comfortable with them. All right, so these are the kinds of activities you should start to get used to being able to do. So you should be able to identify the functional groups in a molecule. So I'm going to circle different functional groups. There's a functional group there, there's one there, there's one there. That thing is a big old functional group. And then a common mistake that some students might do is they might say that that's one functional group and that's a second one. That's not right. The whole part here is one functional group. So as I look over this molecule, it looks like I've circled 5 unique functional groups. So why don't you spend some time making sure that you can assign a label, a category, to all of these different functional groups in the compound. All right, one more slide, and that is we need to start incorporating 3-dimensional information into our bond line structures. You've seen this before in previous chemistry classes. So here is a chain of carbons using that ends and elbows bond line notation. And now you'll notice, let's take this carbon right here. That carbon is tetrahedral, it's sp3, so it has 4 groups coming off of it. 2 of them are other carbons, and you'll notice that they're drawn in the plane of the board here, in the plane of the paper. So that means that the other 2 groups that are hanging off of this carbon must be in the non-paper plane. Here we're showing a chlorine off of that carbon, and it's being shown as a wedge coming out of the plane of the paper. That must mean that the other missing atom that's still on that carbon, which is going to be hydrogen, where is that located? It's going to be wedged back, something like this. All right, and you'll notice the way I've drawn things. I'm trying to show the tetrahedral nature of that carbon. So I've got 2 lines coming down in the plane of the paper, and so then I'll have 2 lines going up that are sort of perpendicular to that plane, one coming out and one going back. So you should be able to identify where in 3-dimensional space the missing atoms off of a tetrahedral carbon need to be. So continuing on this molecule, this carbon has 2 carbons in the plane of the board. It has a chlorine going back, and so the missing hydrogen must be coming out on a wedge. It's coming out of the plane of the paper. Go ahead and draw that in. What would that wedge look like if you were to draw it in? I'll go ahead and draw it in myself, and I might draw something that looks like this. So have it wedged out. Now, whether you have it wedged out going sort of towards the right of the chlorine or towards the left of the chlorine, that doesn't really matter. Keep in mind that this hydrogen, the carbon, and the chlorine, they're actually in the same plane perpendicular to the plane of the board. But obviously, I need to be able to see both atoms, so I'm showing my wedged hydrogen just a little bit offset from the dashed back chlorine. So whether I offset it a little to the right or a little to the left, it doesn't really matter. So you should take some time then to show where the missing hydrogen would be here. The missing hydrogen, where would it be? There, and there, and there. So we just need to get comfortable, not only further comfortable with bond line structure in general, but where the wedges and the dashes would be in these different structures. Okay, that will do it for now. We're going to pick up in class with conversations that have to do with resonance. Now that we are more and more comfortable with bond line structures, hopefully as we start to look at different representations of molecules in terms of how their electrons are arranged, we'll be able to do that with a little bit more comfort. All right, we'll see you next time.